Hello, everyone. Welcome and thank you for joining ARPA-E's webinar on quantum computing for energy innovations. Today, we will be hearing from Program Director Bob Ledoux and Fellow Benjamin Weiner as they dive into how ARPA-E is exploring scalable quantum algorithms tailored specifically for energy applications. The session will consist of a 30-minute presentation followed by a 15-minute Q&A.
Well, thank you, Cindy, and welcome
Dots
everybody. It's great to be here. I'm Bob Ledoux. I'm a
at the
program
bottom of your
director.
screen. The chat feature will be disabled, so please direct all questions to the Q&A box throughout the presentation. Our team will review and select questions to answer during the Q&A set.
Okay, am I ready now, Cindy? Great. Well, welcome everybody. Again, I'm Bob Ledoux, and I'm still a program director at ARPA-E, and I'm joined here by my colleague.
Hi, everyone. I'm Ben Weiner. I'm a fellow here at ARPA-E.
And today we would like to discuss with you the role of quantum computing in energy innovations. This presentation does not constitute a funding opportunity or solicitation. So let's start with an overview of the proposed potential program. First, the focus of this program would be to leverage quantum computing to transfer chemistry and material science into fully predictive tools for energy innovations. I know it's quite ambitious. What's the opportunity and why now? Well, quantum hardware is advancing rapidly with significant capabilities expected in the near term. Now, we believe that to fully leverage these breakthroughs, it's crucial that energy applications and algorithms keep pace. And our approach in this potential program is to develop scalable, and we'll return to that often, quantum algorithms for energy-centric chemistry and material science applications. And we're going to focus the technical aspects on the optimization of the full quantum computational stack. And the program outcomes that we hope for here is that we can unlock early quantum advantage, and this will accelerate innovations across the full ARPA-E portfolio, and we hope for many, many other fields also. And we hope by doing this potential program, that we'll really get on that disruptive quantum curve in which we take many problems that are not solvable classically and be able to accomplish them rapidly and accurately. Next slide. So many of you may be new to ARPA-E, and when we talk about scope of applications, it's important to understand what ARPA-E mission areas are. Obviously, it has to do with energy, but the 5 focus areas are to reduce imports, to reduce emissions, notably greenhouse gas emissions, improve efficiency of energy systems, as well as to improve energy infrastructure resiliency and improve in radioactive waste management. So any application that could be proposed under this potential program needs to hit one of these areas. We're confident that many applications in quantum computing for chemistry and materials do just that. Now, how did we get to where we are now? And this is just a snapshot of events in the last year. But we got here, as in many other ARPA-E programs, by really reaching out to stakeholders, analyzing what is really white space in energy simulations, chemistry, and materials. And a notable meeting was the workshop on quantum for climate and sustainability, in which we really emerged from that believing that chemistry and materials do hold the promise that quantum computing can really give us, eventually at least, exponential speed up. And we believe this is consistent with the DARPA benchmarking analysis to date. We've reached out to our colleagues at DOE, DARPA, academia, as well as many, many other commercial interests. And we held a workshop in April, and there, what we formulated was that the best place that ARPA-E could make a difference here was to really focus on the software side, and that is optimizing the full computational stack. And to do that, we equally realize, and that we're so glad to have so many of you here, is that we really need to bring together interdisciplinary teams to tackle a problem that spans the full computational stack. So that sets us up for what it will be, we believe, the technical focus for this potential program. We're focusing on, as you can see, the top two layers here, which are the applications and algorithms and software. And the technical focus really spans that. So applications need to be in ARPA-E's wheelhouse. We just described those. There are many existing quantum chemistry applications, algorithms that need to be brought into the full quantum regime. And we hope there is discovery here too, that many new quantum chemistry material algorithms can be developed. Now, of course, we need to then the team needs to generate an optimized solution for quantum circuits. And as we go closer to the hardware, then we would very much like to see the team integrate any optimizations or co-design into the error correction and any other optimizations for hardware. And an integral part of this will be how do we test and validate these new algorithms. And we will, as we'll see, really require that you run them on a quantum computer and really strive for scalability and validate against experiments or possible emulation on a classical computer. Once again, trying to drive us onto that scalable quantum curve for chemistry and materials. So we have to compare this to the very, very powerful state of the art in quantum chemistry today. And there's kind of two basic approaches. One is what we'll call the wave function theory, which is basically the exponentially growing and resource model, but it's very accurate, but classically it's not scalable. Now, the workhorse, particularly for a ground state energy estimation, is density functional theory, which is very scalable, but in many cases is not accurate. And since it is difficult to predict when it is accurate or not, this really leads to problems with predictive power of that technique. Next slide. So to give you an example of what the state of the art in the full wave function, in this case, a full configuration interaction calculation, it is quite a tour de force in classical computing. I mean, I highlighted 10 to the 12th determinants. So this is really stretching a lot of classical resources. And if you look at the scaling curve for such a classical calculation, really adding just one more orbital makes the resource requirements go up a factor of 10. So I think it's fair to say that for such calculations, Moore's law will not fix this. You know, you just can't make enough transistors to make all this work. So what we're hoping for, and we'll hope you will be partnership in, is really using quantum computers to do quantum chemistry, which is one of the founding reasons why quantum computing was first suggested by the likes of Richard Feynman. Okay, so next slide. So we do not anticipate funding within this potential funding opportunity hardware, but we need to be cognizant of where we think quantum hardware will be within the period performance of this potential program. So these are just some public, relatively new roadmaps. But what I want you to take away from this is that there's a lot of potentially shots on goal to reach in, say, by 2028, 2029, 100 or hundreds of logical qubits. And logical qubits are virtual, quote, qubits that are made up of physical qubits, which include error correction. And we're not defining the level of error correction here, but we will use the term logical qubit for error corrected, computationally useful qubits. Okay, so now we look at the status of algorithms in chemistry and materials. And this is not an exhaustive look at the literature, but it contains some examples of resource estimation. And you can see for catalysis, for battery materials, corrosion, and so on, you see that the logical qubit count presently estimated to do such problems at high accuracy are in the thousands, not in the hundreds, in the thousands. And this sets the stage for why we are focusing on optimizing the full computational stack. Because what we would like to see this program do is basically basically with the rapid advances in quantum hardware, which are hopefully going to get us into the hundreds of logical qubits and beyond, what we will focus on is taking the algorithmic resource requirements and driving those down to meet the hardware in this period of performance such that we get significant scalable results that beat the state of the art in quantum chemistry and materials on that. Now, this may be fine-tuning existing algorithms. It may be coming up with totally new algorithms that hit different parts of the chemistry and material science applications. Next slide. So, what may be promising areas in this quantum computing applications? Well, you know the scope already that's required for ARPA-E, but I think it's a combination of realizing where the quantum hardware resources will be, combined with we want provably, demonstrably scalable solutions. But we equally want to look not just in the existing space against the state of the art, but really always looking for novel and important applications in quantum chemistry, which may involve things like time dynamics and excited states, right? Maybe loosening the Born or getting rid of the Born Oppenheimer approximation. Look for electromagnetic interactions, looking for things that involve many multiple excited states, multi-scale correlation. So we hope that we can really excite you such that we see potential applications throughout this space. So some examples we will mention, and Ben's going to give you examples following this summary, is that in chemistry, we talked about catalysis a lot, has many applications. Batteries, it could be new anode materials, just completely new battery chemistries, corrosion, synthesis, reaction dynamics. Light matter interactions, again, with quantum computing may shine in things like time evolution, looking at excited states. Actually, metrology. We have many, many very powerful metrologies, but we often have trouble interpreting what the molecular structure is they are revealing. And then, of course, we haven't mentioned yet spin systems, right? Finding new magnetic materials that are based on Earth-abundant materials. And of course, one of the holy grails is room temperature superconductors. And all of these span different ranges between static kind of calculations, ground state energy, say, and dynamical things, dynamical potential algorithms such as reaction dynamics. So when you put all this together, you may ask, what's an example maybe of what success looks like? So let's take a problem, catalysis, for ion-based catalysis for CO2 hydrogenization, which has been very well studied in simulation framework on classical computers. What success would look like, I think for sure, in such a program that we would be proposing is that certainly you reach it in quantum algorithms on a real quantum computer, the state of the art that classical computation can do. And you move it, would be great within this period of performance, into a new regime. For example, in this case, reaction dynamics. And if those algorithms are run and proved to be scalable, then of course we would understand that as the quantum computing hardware capability grows, we would be reaching into areas of real discovery that is not possible at all with the present state of the art. So reducing all that to some concept of what metrics may look like for such a program. First, again, we start with the primary metric, which has to be it's in scope with ARPA-E, and hit a metric of interest, of importance to us. And these are metrics like quad scale energy reduction, maybe not in the first application, but it can lead the way, or gigaton scale emissions reduction. So that's an important focus. We would want to see optimization and co-design across the full computational stack and deliverable that must be performed on a quantum computer and show transformative scalable capability against the state of the art with significant improvement like 100x's, or if you have to demonstrate it on a smaller dimensionality thing, make a clear path to the near term to full scalability. And we'd have to provide a manner, a method of validating either against experiment and classical benchmarking. And we have not had time to spend to mention here, but all ARPA-E programs have a clear tech to market approach. You know, if it works, will it matter? And this will also be a key component. So with that as an overview and something of a summary, I'd like to turn it over to my colleague, Ben, who will give you some examples.
Bob, and thank you all for being here. So I'm going to spend the next few minutes talking through some example energy applications of quantum computers. Two things that I want to emphasize here. First is that these are just examples, and in a potential program, we'd be very excited to see ideas that aren't discussed here. And the second is that these are energy applications. Bob just said it, but it's important enough that I'll say it again. The primary metric in any program would be impact on ARPA-E's mission areas, and so any application has to have a very strong connection to energy impact. So the first example we'll dive into is catalysis. So catalysts are materials that let us control the rate or direction of a chemical reaction, and these are important because the chemical and refining industries are responsible for about 12% of US emissions. And if we're going to reach our goals with the transition to electrochemistry, the bioeconomy, CO2 utilization, we're going to need a lot of catalyst innovation in the coming decades. And so there are very diverse catalyst systems which have been studied computationally using both classical and quantum algorithms. We're going to zoom in on the example of using ruthenium to reduce CO2 to methanol, which is a valuable platform chemical. So chemists believe that this reaction takes place in 8 different stages. And if we want to understand it and improve it, we need to understand the transitions between these states and therefore their relative energies. And unfortunately, classical computers simply are not accurate enough to do this. If you want to do real practical chemical engineering, you need accuracies of about a millihartree. That's close to a kilocal per mole, or chemical accuracy. And if you look here at this plot on the right of the energies that you get from density functional theory, or DFT, you see that you get differences of 20 times that with no way to distinguish between them. So the tools that we have today simply are not accurate enough. So I want to step back and look at how this calculation fits into a workflow for a couple of reasons. And the first is that we recognize that doing a single calculation is not going to be enough to make a better catalyst. And so in a project, we'd want to really understand what the full R&D workflow is and how your calculation is really going to drive a difference in the long term. And the second is that we believe that for the foreseeable future, quantum computers are going to be used in a hybrid quantum classical workflow. And so we want to understand what that handoff is. So in this example, you might start by defining all of the structures. Then you would identify the active space, the configurations that you think are really important. You do the ground state energy estimation that I just discussed. And then you feed that back into a kinetic model. Perhaps you update your structures and you iterate. And so today, we use density functional theory to figure out these energies, but in the future, we want to use quantum computers. And there's been a lot of progress in quantum algorithms for ground state energies. So in just the past 5 years, we've seen the resource estimates for the number of logical qubits you need come down by a factor of 2. We've seen the gate estimates come down by a factor of 10. But remember, if we think that near-term hardware is going to have hundreds of logical qubits, we still need a 10x improvement in those algorithms if we're going to run them. And so where are we going to get 10x? Again, we think it's from optimizing through the full computational stack. That means new approaches like moving to first quantization, new algorithms, new embeddings to the hardware, and so on. And here on the right, I've plotted the resources that we think you need to achieve a certain amount of accuracy, a certain number of orbitals with the current algorithms. You see that right now you would beat the classical limit at around 1,000 or 2,000 logical qubits. We think that in a program you could get that down by a factor of 10 and really be able to use quantum computers to change the chemical industry in the near term. The second application, it's one that the physicists in the room will be very excited about, it's high temperature superconductivity. So superconductors are so named because they conduct electricity with zero resistance. And if you could deploy these widely, the impact would be tremendous. You could have lossless energy transmission and storage, powerful magnets for MRIs and fusion, highly efficient electronics and motors. The list goes on and on. But unfortunately, even so-called high temperature superconductors still operate at very low temperatures, around the temperature of liquid nitrogen, or at very high pressures. And the materials tend to be very brittle and very hard to use for engineering. And so what we would love to do is use quantum computers to make better superconductors. So let's look at a workflow. The high TC superconductors that we know are very complicated. And so we think you'd want to start by systematically simplifying that model to something that is more tractable, like the Fermi-Hubbard model. You'd then want to study the Fermi-Hubbard model to understand the physics, use that physics to predict new materials, and then iterate. But the challenge is that even though the Fermi-Hubbard model, it looks very simple, right? It's simple enough to put on a slide, but the physics gets very hard very fast. There are strong electron-electron correlations, strong fluctuations. We've been studying this model for 60 years, and I would say that we barely understand the ground state. And so there have been some truly heroic, classical computational efforts recently trying to understand the Fermi-Hubbard model. And I say that these have really given us more evidence that the physics of high temperature superconductivity is lurking somewhere in that model, but unfortunately, these efforts are simply not scalable. In contrast, there are quantum algorithms for studying Fermi-Hubbard, where the number of qubits that you need grows quadratically with the lattice size. It's very reasonable, and they have a constant circuit depth, so that's a constant runtime. And so just using the algorithms that are published, you reach quantum advantage at close to 1,000 logical qubits, and we think that in the course of a program, you could bring that down to near-term hardware to really use quantum computers to design better superconductors. And finally, I want to end by talking about excitations and time-dependent phenomena. I would say that for these previous two examples, these are areas where we have classical methods that simply aren't good enough. And now we're moving into territory where you really don't have good, mature classical options at all. So thinking about excited states in the energy space, one important area is X-ray absorption spectroscopy, or XAS. XAS is a really powerful tool for materials diagnostics. So in the example given in this paper, say that you're trying to design a battery and you want to understand the degradation mechanisms of going from a lithiated state to these three different delithiated states. You want to know which process is relevant. So you do XAS and you get a spectrum. And the challenge is that now you have to compare it to something. And the options that we have for doing this classically are simply not very good. If you use the state-of-the-art, time-dependent density functional theory, the spectra that you predict are missing a lot of the features that actually tell you the useful information. In contrast, there is now a quantum algorithm for calculating these absorption cross-sections directly by simply calculating the matrix elements between the excited states and the ground state. And so in this very first paper, they estimate for that smallest relevant example, you need about 900 logical qubits, and they make some arguments for how you could bring that down. And so we think that this is a really exciting area for near-term quantum advantage. And now I want to end by talking about dynamics, because quantum computers really unlock fundamentally new ways of approaching problems that you couldn't even have imagined with just a classical computer. They let you very naturally couple your problem to light, to external fields or thermal baths. They let you go beyond the Born-Oppenheimer approximation to really look at those nuclear degrees of freedom. They let you think about ionization and scattering, or even look at direct reaction dynamics. And so there was a really wonderful proof of concept paper last year where they simulated a quantum computer on a classical emulator and looked at the time evolution of a 3D helium atom. They didn't have to do any fancy moving to second quantization, trying to choose the active space very carefully. They could simply set up the problem on a grid and watch the wave function evolve directly. So very direct, very efficient, and very elegant. And so these new methods really could unlock new energy applications. Everything from better photovoltaics to understanding material synthesis to better photochemistry or an understanding of corrosion. Two that I want to talk about briefly. There was recently a paper on a quantum algorithm for calculating the stopping power of a charged projectile in a plasma. So this is relevant for applications like inertial confinement fusion, as well as understanding radiation damage in nuclear reactors. And this is a purely dynamical process. There's really no good classical option for calculating this. A second example comes from that paper with the helium atom, where they directly looked at the ionization and the scattering dynamics of electrons interacting with each other. And again, you didn't have to frame the problem in some very complicated way. They were able to just set up the wave functions and let them evolve. And so we believe that, because quantum computers let you approach problems in these new ways, they could potentially let you make an impact in energy in entirely new areas. Now I'll turn it back to Bob.
Thanks, Ben. Thanks for those great examples. So just a couple closing slides here. So you may ask, what does a team look like, and maybe how do they get integrated into basically optimizing the full computational stack. This is a completely made up example, no real names here. And so we would think that an ideal team would have applications expert or an application expert on any particular problem that you're trying to solve. So in this case, maybe that comes through a chemical company that's doing a new catalyst on that. Working into the quantum computer algorithmic regime might be a software company, could even be an AI company that's moving into quantum or purely quantum algorithms company. And then we have hardware, a particular quantum piece of hardware that has to be done. I think working intimately with a quantum hardware provider might be very important to this. But as you can see, we want all levels to be co-designed and optimized. So although there is clearly a closer connection between the chemical company and the software company, nonetheless, we believe that integration, looking at each level and iterating through that stack, is really where we're going to get that factor of 10 in resource reduction, or completely new algorithms that get efficiently incorporated into the quantum stack. So that's an example of what we think a team may look like and what some of their tasks are. Next and final slide. Okay, so this is just a summary, I hope, of everything we've tried to discuss concerning this potential funding opportunity. But first, on top of the full stack is, of course, identifying chemistry and materials problems central to ARPA-E's mission. We've discussed what that is in general, our 5 mission areas. I think a successful project needs a fully integrated team across the full computational stack. We really want quantum algorithms that have a dramatic and validated increase over the state of the art. We realize that if there's not a direct comparison to the state of the art, that basically you give us your idea of how it's validated. We really are leaning on proof of scalability here for a couple of reasons. One is, and most importantly, is that if you solve the problem at whatever dimension we want to know that it'll be applicable in the near term as quantum resources are basically improved over time. And I think fundamentally that scalability will allow us to evolve other algorithms that, again, we know grow with the quantum hardware resources. We do want it to be performed on real quantum hardware. So I think working closely with a quantum hardware vendor is key, and we will ultimately need to see a clear path to market. So with that, our presentation is the end. I thank you for your attention, and now we will open it up to questions. So put your questions, as it said, in the little ellipse pops up a question and answer box, and from there we can see potential questions. So I see some are already in there. Please add any that you have. So I'll take the very first one, which is, to what extent are algorithms which do not require error correction considered in scope? Great question. So no, I don't think they will be in scope. I think what's more important here is that it solves a problem of interest and it is scalable. So I don't think we'll have any requirements on the error correction other than that you get an improvement of the state of the art and it is a scalable solution. I don't know, Ben, do you have anything to add to that?
No, I think that the scalability is key. And, we've heard exciting things that people are doing with analog quantum computers, for example. If there's a scalable example of that, that's great. We want to solve the problem.
Exactly. Okay, I'll move on to another one. Is having a hardware partner in the team critical? I would say yes, but I think the only strict metric will be you need to run it on a quantum computer. But I would probably say that, well, I would say a partner, you need to run it on a quantum computer. So in as much as you will need access to the proper amount of runtime, say, on a quantum computer, I think that is very relevant. But a partner, I think not strictly speaking. Ben, what do you say to that?
As long as you can meet the requirement of executing on quantum hardware, that is the important thing.
Agreed. Agreed. Okay. The next one I see is your example project has all industry performance companies. Oh, will a team consisting of academics and national? So sorry about that. We just gave one example. Absolutely. I would say at ARPA-E, my experience is basically we do cooperative agreements, so there must be a private entity along the road as part of the team. But I would say a lot, many, maybe half of basically our projects have a full team from academia, national labs, and a commercial interest on there. So that is absolutely in scope and actually at some level encouraged. So yes, for sure. I'm looking down the next one. Do you have a time estimate for when to anticipate a funding opportunity being issued? Well, we can't give out until it's done. It's not done. But I would say that with this webinar and collecting your feedback from stakeholders on this, I think that we would certainly try to very quickly move to a potential funding opportunity. And I would advise you to always make sure that you get the ARPA-E newsletter, which always is one of the first to announce new funding opportunities. Okay, let's see. I'm just moving down through the list. Okay, this discussion is presented in the context of a fault-tolerant quantum computers. Could you comment on NISC and analog quantum computing? Well, I think that Ben already said for sure. We are not prescribing that it must be, quote, in the fault-tolerant regime. So NISC and analog is in scope with the two caveats I think we've already mentioned, that it is a scalable solution, basically, and it does have significant improvement over the state of the art, and obviously is in scope and ARPA-E important metric and so on. Ben, do you see one that you want to take here as I look down through the list?
We have a couple on estimates of the length of the program.
Yeah. So on that, once again, partially TBD, but I would say if you look at our website, oh, and by the way, I will say, if you go on ARPA-E Exchange, you can look at every FOA I think we've ever done, or certainly all the recent ones, and you'll get a good feeling for what the period of performance typically is and what sort of award sizes are. But I would say really the vast majority of ARPA-E programs are in the 3-year period of performance. And of course, we always allow 4.5 plus ups and so on. But the period of performance, I think the sweet spot has been historically 3 years period of performance.
We have a question: how will the success of the whole program be measured? Publications, software products?
Oh, so this is one we at ARPA-E love to get. So remember, I didn't show my last slide. If it works, will it matter? So I think one thing that ARPA-E, and I think actually was the way we were stood up, is that there's a premium on having a path to get to market, to get to the marketplace, to get to deployment as quickly as possible. So I would answer that in 2 distinct ways. One is there's a clear path that this can be commercialized and make a difference as soon as possible into the commercial space. The second is the application, if successful, accelerates an important metric against our mission statement, like reducing greenhouse gases, saving energy, doing a better waste mitigation. So it's that combination of success to us is we solved the problem, and we solved the problem as quickly as possible. And that is and we're perfectly happy if people make money doing it. So we really want to have it see the light of day. And I don't mean to say this in a bad way, but we don't really encourage science projects. We want solutions, I think, is a summary. I don't know, Ben, if you have anything to add to that.
No, I think that says it all. We had a question: Does the hardware execution need to be performed at scale, or will proofs of principle be sufficient?
That's a
This
great.
comes back to this. Yeah, this comes back to the scalability issue we've been talking about.
Yeah, you
Look,
can answer that, Ben. That's exactly the answer. Yeah.
yeah, we would love if in a period of performance, you can demonstrate a transformative capability relative to state of the art. We understand that given the hardware, there's some uncertainty about what will actually be available, at the end of a particular period. And so if you can show something that has the potential on slightly larger hardware to be transformative, that is okay too. But that's why we're okay with proofs of concept as long as they're highly scalable. And I want to emphasize that they should be able to show that impact not on some theoretical machine in a decade, but like say 3 years after a program, right? We're looking for like pretty short to medium term advantage.
Exactly. Great comment. Okay, I'm looking at another one. Does this problem must tie to chemistry and materials only? The answer to that one is yes. In scope, we'll be addressing a materials and chemistry problem. So for example, just pure optimization, which could be a part of solving the chemistry and materials problem, but not just, for example, a pure optimization problem by itself. So I think the scope will be very focused on chemistry and materials only. Good question. Let me see. How are you deciding what quantum computing hardware vendor you want to partner with? Well, we're not deciding anything on that. I think that is completely up for any applicant to submit on who they want to work with. So we're completely open to that. Again, I think that you have to run it on a quantum computer, and we do want optimization down the stack, but it's really going to be, it's really going to be up to the applicant to decide how intimately they want to work with a quantum hardware vendor. So I don't think we will make any prescriptions on exactly who or how you do that, other than you run on a quantum computer. Ben, did you have anything else to add to that?
Yeah.
Okay. What type of institutions will be allowed to be lead organizations or prime? Okay, well, this is always a subtle thing. So we would anticipate this is a cooperative agreement. So it does have to have a private entity be the prime. But we understand that the lead could very much be a lab, etc. So I think that again, the prime if it's a cooperative agreement is a private institution. And of course, please look at the forward if I'm not saying this correctly, but I think that's the case. But the lead can definitely be, like, for example, you have an FFRDC can definitely be a lead in this, and that is not uncommon. Again, for examples of that, you can just look at our website for existing programs. I, for example, have a program called Onwards. You can look at the mix of institutions on that. Okay, Ben, have you seen another one you want to bring up? Just scrolling back down.
Yeah, there was a multi-part question which asked, I think, two relevant things. One is, how many projects can one company be a part of as a sub? And with a follow-on, what are the restrictions on foreign participation?
Okay, great. Two great questions. So, to the best of my knowledge, a particular performer can be on any number of projects as long as, obviously, it does not exist a sum rule for the amount of time the person can spend. So I don't think there's a prohibition against that at all. You said it was a three-part question. Well, again, what was the second one?
Foreign participation by foreign entities.
Yes. So again, we can have foreign entities participate in this program. If the work is done or the purchase is done non-domestically to the U.S., then you do have to get a foreign work waiver. And that does happen, and that is possible.
There's a question about how this relates to the DARPA programs that we touched on earlier. So US Q2C, as well as the new quantum benchmarking program are hardware focused, right? So we're not funding hardware development. So that's a major difference. And then the DARPA quantum benchmarking program was essentially about doing a survey of what problems are impactful and practical, whereas we are trying to choose specific problems and actually solve them.
Exactly. Excellent. So we're very intimately related, cross-pollinating, part of the same very important community driving this forward. But I think that was a great answer, Ben. Okay. I see one here that's important to answer. A hybrid quantum approach is acceptable. Yes. Simple answer is that yes, and we anticipate there will probably be many of them on that. Okay.
There was a question on project size and cost share. And I think the answer again is that nothing is out until it's out. You can look at past FOAs to get a sense of the scale of projects and what the cost share requirements have looked like. If you just look historically, ballpark, a typical ARPA-E individual project has been $3 to $5 million, but there can be quite a range. So you just have to look at past examples and wait until a FOA would come out.
Yeah, I think if you look at some, that's a great point, Ben. If you look at some recent examples that have come out of large programs at ARPA-E, I think it'll give you a sense of the total funding opportunity, and it'll give you a sense of what the distribution of funding per project is on that. And cost share expectations depend on the entity that is part of that cost share. So again, that will be explicitly done in the FOA. And again, you can look at existing examples. The FOA will obviously set it out. But basically, as you can imagine, a large, quote, large company has a larger cost share than a small company. And if we put out an SBIR component of the project, that has no cost share. I have someone on contracts is on, correct me if I'm wrong, but I believe SBIRs do not have a cost share, for example, a small company. Okay, any other one, Ben? Is there another one that's a particular?
An interesting one. Are there benchmarks the solution would be held to?
I do not believe we would put in fixed benchmarks, but when you compare to the state of the art and show your improvement, it would have to be against either a high fidelity, say higher accuracy, classical simulation, or an experiment, for example. Would we put in specific benchmarks? I think given the breadth of what we're proposing here and putting in scope, that might be difficult. So probably not leaning that way. Ben, do you have any thoughts on that?
No, just that I think again, it would be hard to come up with a single benchmark for comparing the Fermi Hubbard model to like nitrogen reduction or something like that. And so it's really the onus would be on the teams to figure out that yardstick and then set a goal that's really bold enough for sort of the ARPA-E high risk, high reward orientation.
Yeah, I think that's a great answer. I mean, basically, the art as well as the science of trying to write a funding opportunity that really pushes the field forward is to try to leave it prescribed enough that the focus is clear, like chemistry and materials, but not trying to dictate the solution. And so, as Ben said, therefore, it is somewhat difficult to have very specific benchmarks. So, we will try to write in general metrics that we describe some of them here, but probably not give very exact specific benchmarking that could possibly exclude some very clever and innovative solutions to that. Okay, well, we're at time. I noticed that there was a clarification to the foreign entities that is put in the that has been put into the question and answers that describes it more fully. Please take a look at that if you're interested in that. And otherwise, I guess since we're at time, Ben and I would like to thank you for your attention. I would like to thank many stakeholders who are on this call and are not that have provided so much input. And I can't tell you how excited we are to hopefully get this thing launched and really work with you to address this incredibly exciting and absolutely transformative field. So thank you for your attention. Have a great day.